Let's begin with a quick reality check. Most modern applications these days run on containers. Why? Because they're lightweight, portable, and make it easy to scale and isolate different parts of an application, whether it's a backend service, a database, or a work with it. But here's the catch. While containers give us flexibility, they also create a huge resource allocation problem. Every container needs just the right amount of CPU and memory. Too little and it crashes, too much and you waste resources. And the truth is, most orchestrators today just aren't smart enough to get it right. They rely on static limits or slow, coarse grained adjustments based on historical usage. And when the predictions fail, you get throttling, out of memory kills, and a lot of underutilized infrastructure. That's where this work extra comes in. ESCRA reimagines resource allocation in container environments. It's a lightweight, event driven system that reacts in sub-second intervals, based not on outdated metrics but on live telemetry from the kernel. And the best part? It works on top of Kubernetes. Hence, it requires no container restarts and is built for high performance single tenant applications. So, here's how ESCRA operates. ESCRA has the application deployer that reads YAML config files, sets global resource caps, and launches containers. The controller maintains live state. It creates logical container objects, stores telemetry, and reclaims unused memory. Then, the resource allocator makes fast, lightweight decisions based on telemetry and event streams. On each worker node, an agent hooks into the Linux kernel using a custom syscall. It tracks CPU and memory usage in real time and enforces new limits without restarting containers. These components together form a tight feedback loop that allows ESCRA to act immediately when a container is overloading, underperforming, or approaching out of memory. Let's take a deeper look at how this architecture works in practice. Once a container is launched, the container watcher detects its deployment by the Kubernetes API and immediately notifies the agent running on the same worker node. Then, the agent executes a custom syscall that sets everything in motion. First, it sets up a persistent TCP kernel socket to the controller so that the container can send events like out of memory warnings instantly. It then hooks into the Linux completely fair scheduler and collects detailed CPU telemetry each period. Particularly, it collects actual runtime, throttling status, and unused CPU time. And finally, it hooks into the memory C group subsystem to catch out of memory events just before the kernel would kill the container. All of this runs in the kernel, meaning ESCRA gets telemetry and critical events with almost zero latency and minimal overhead with no polling and no expensive logging. Now let's talk about how ESCRA turns that raw telemetry into decisions fast. The resource allocator runs on a per period basis, in some configurations as frequently as every 100 milliseconds. For CP scaling, it uses two sliding window statistics. First, it tracks how often a container is throttled, and second, it tracks how much unused CPU time it's leaving on the table. If a container is being throttled often, ESCRA increases its quota for the next period proportionally, and only if there's spare CPU available in the global pool. If it's underutilizing CPU, the allocator gently scales the quota down using a tunable decay factor that avoids overreaction. For memory, things are even more interesting. If a container is about to exceed its limit, the memory C group hook triggers an out of memory event which is forwarded over to the TCP socket. And then the allocator checks if free memory is available. If yes, it immediately increases the limit. If not, it instructs the controller to reclaim memory from containers that are using less than they were allocated, using a safety margin buffer to avoid premature eviction. Apart from this reactive behavior, ESCRA also proactively keeps checking for the memory usage of each container. If it needs more memory, then it allocates from the global pool. And if it's underutilizing the memory, then it reclaims the memory from that container and adds it to the global pool. This feedback control loop allows ESCRA to balance workloads dynamically across a single application. From the evaluation, it was also observed that ESCRA consistently delivers better performance than both autopilot and static allocation across a range of workloads. It achieves significantly lower latency and better resource utilization, as shown by performance plots and Slack CDFs. Even in the rare scenarios where ESCRA slightly underperforms, the difference is minimal, and the overall slack, that is the buffer between usage and limit, remains consistently improved, that showcase ESCRA's stability and responsiveness under pressure. Thus, ESCRA is a new class of resource management that responds faster than anything that came before. Thank you.